Today's lesson is on trig substitution, and we use these in three cases. If we have the square root of a squared minus x squared, the square root of a squared plus x squared, and the square root of x squared minus a squared. So how I want you to think about this as making a right triangle, and this, based on the Pythagorean theorem, is one of the sides. So the three cases, so square root of a squared minus x squared. That means this piece is going to be a leg, and since the a is first, the hypotenuse is a. So I'm going to make a triangle here. Okay, this is going to be theta, and relative to theta, we said the hypotenuse is a. So either of the sides can be this leg, but this one's going to be a trig substitution for sine. So I'm going to let this equal x, which makes this, according to the Pythagorean theorem, a squared minus x squared. So here, sine of theta is going to equal x over a. So I can solve for this x. X is going to equal a sine theta. And that would be the substitution we would make. This next one, a squared plus x squared, means that this is the hypotenuse. So this is the square root of a squared plus x squared. The two sides are x and a, and we're going to be using tangent for this one because we're using the two sides. So this will be my x, this will be my a. So tangent of theta is equal to x over a, and then again we're going to solve for that x. Okay, the last one is like the first one but switched. So this is a leg where the hypotenuse is the x. We're trying to get a over x again. This one's going to be secant because we want the hypotenuse in the top, and in this case the adjacent side. So secant of theta is equal to a x over a, hypotenuse over adjacent. And so again, x is going to equal a secant of theta. Now these are not something you have to have memorized. Anytime that there's been a trig substitution on an AP test, they tell you what the substitution should be, but we're going to go through a few examples. Okay, this first one here does not require a trig substitution. It's just going to be a regular U substitution. We're going to let U equal 64 minus x squared, and we know that because this one's derivative is sort of outside. So du is going to be negative 2x dx. So my 2, this is a definite integral. So we're going to plug in 7. So 64 minus 49 is 15. We plug in a negative 2, and we get 60. I need a negative 2x here, which means I need a negative 1/2 on the outside. My new bounds are 60 and 15, and we have the square root of u du. I'm going to rewrite this before I integrate as positive 1/2 and switch these around. 15 and 60. This is going to be square root of u. So that is 1/2 times 2/3 u to the 3/2. So that will be 1/3 when we cancel those 2's. 60 to the 3/2 minus 15 to the 3/2. This one we can do really without doing calculus because we know this is going to be a semicircle. So this is going to be here, and I'm doing the integral from -8 to 8. So I just need this area, which is going to be 1/2 pi r squared, which is going to be 8 squared. So we're going to have 64 divided by 2, which is 32 pi. This one we will be doing a trig substitution. So this is in the form a squared minus x squared. So the first thing we're going to start here is with a triangle. I'm going to make this theta. If this 64 squared minus x squared means that my hypotenuse is going to be 8, thinking about the Pythagorean theorem. My x is going to go here, and this side is 64 minus x squared. Okay, we'll be using this triangle several times during this problem. So in this triangle, sine of theta is equal to x over 8. So x is going to equal 8 sine theta. And that's the replacement we're going to make. But if we're going to make this replacement, we also have to get rid of the dx. Because if I had this as theta and this is x, that's a problem. So dx is going to get replaced with 8 cosine theta, d theta. So this is going to be the integral. 64 minus 8 sine theta squared times d theta Okay, so now we just start simplifying until we get something that we can integrate. Put this 8 out front. So this is going to be 64 minus 64 sine squared theta under the radical times cosine theta, not in the radical. I'm going to factor out the 64 here. Which leaves me with 1 minus sine squared. Okay, so square root of 64 is 8, so I'm going to multiply that 8 with that 8, so we're going to have 64 on the outside. On the inside, I'm going to have the square root of, well, 1 minus sine squared is cosine squared. Square root of cosine squared is cosine. So now we have the integral of cosine squared theta d theta. When we're doing the integral of cosine squared or sine squared, we're going to use the double angle replacement. So that's going to be, for cosine, 1/2 cosine 2 theta plus 1, or 1 plus cosine 2 theta. And then that's what we integrate. Okay. Zoom out there to give us a little bit more space. All right. So 64 and 1/2 is going to be 32. Then we're just integrating this and this. So 32, the integral of cosine 2 theta is 1/2 sine 2 theta. Integral of 1 is going to be theta. Sine 2 theta is an identity that we learned in pre-calc, is 2 sine theta cosine theta. So we have 32 sine theta cosine theta plus 32 theta. Now we have to go back to the triangle and write these things in terms of x. Okay, so we're going to have 32 times sine of x is still going to be x over a, x over 8. Cosine theta is going to be the adjacent over the hypotenuse. So cosine of theta is going to equal root 64 minus x squared over 8. Theta, in terms of x, there's a couple different ones we can do, but the simplest one, theta in terms of x and 8 and in this triangle is going to be the sine inverse of x over 8. So these are pretty involved. You, again, typically won't see a full trig substitution, but I wanted you to see how that works. All right, these last two, this one we won't need a trig substitution, this one we do. We don't need it here because I can let u equal 4 plus x squared. So du is 2x dx. There's your 2. So this one is the integral of dx du over the square root of u. So rather than writing the 1/2 out front, we'll go ahead and put it right there with the 2, because that makes this integral the square root of u, which is going to be the square root of 4 plus x squared plus c. This one, however, I don't have that x to use for the u substitution. So this one is going to be a trig substitution. And again, you're thinking about this as a right triangle. The square root of 4 squared plus x squared means that 2 and x are the sides, and our hypotenuse is the square root of 2 squared plus x squared. So tangent of theta is equal to x over 2. 2 tangent theta equals x. And that's what we'll substitute in here. dx is going to be 2 secant squared theta. All right. So here we're going to have the square root of dx is going to get replaced with 2 secant squared. And in the denominator, we're going to have the square root of 4 plus 2 tangent theta squared. All right. And one of the reasons to do a trig substitution is there's so many different identities that we can use, that we can manipulate trig formulas a lot easier than a lot of just plain algebraic equations. All right. So we'll factor out that 4. So we're going to have the square root of 4 times 1 plus tangent squared. This is an identity. So we're going to have 2 over the square root of 4, which is 2. So those are going to go away. So we're going to have secant squared theta over the square root of 1 plus tangent theta is secant squared. And remember, that comes from sine squared plus cosine squared equals 1. Dividing all of those by sine means we have 1 plus tangent equals secant. Square root of secant squared is going to be secant squared divided by secant is going to be secant. And we know the integral of secant is the natural log of secant theta plus tangent theta plus c. So then we go through and make those replacements for secant and tangent. So secant is going to be the hypotenuse over the adjacent. So that's going to be the square root of 4 plus x squared over the adjacent, which is 2. Tangent is still x over 2 plus c. So again, trig substitution is not something you necessarily need to know for the AP test, but they're kind of a cool little trick on how to do various integrals.